sulfurous acid. We need to add up how many electrons. And so the hydrogens have 2, since there's 2 of them. Sulfur has 6 valence electrons. There's 3 oxygens, and they have 6 each, for a total of 26 valence electrons. We are mainly just going to draw simple molecules from scratch this semester. And an acid is the most complex from scratch we draw. So you have to recognize that it's an acid. So it's an oxyacid. It looks like hydrogen is bonded to sulfite. That's what it looks like. And so when it's an oxyacid, when you put the atoms on the paper, the hydrogens are going to be bonded to the oxygens. The oxygens are bonded to the sulfur. And so when you put the atoms out, sulfur would be in the middle of the oxygens. And then the 2 hydrogens would be next to 2 of the oxygens. Then you start doing bonds and dots just like before. So you just choose an outer atom. I would choose the most outside atom, which is hydrogen. And so hydrogens are bonded to the oxygen, and hydrogen just gets 1 covalent bond, and that's it. So then if you move on to the oxygen, so I'm just going to do this oxygen first. It already has 1 bond, and oxygen wants a total of 2. So it can be formal charge of 0, but it also needs 2 lone pairs. So that oxygen there has 2 bonds and 2 lone pairs. This oxygen here will need 1 more bond. It's got to connect it to sulfur. That gives it 2 bonds. And then it needs 2 lone pairs. This oxygen only is bonded to sulfur. So both its bonds go to sulfur. And then it has 2 lone pairs. So each of the outer atoms is drawn so its formal charge is 0. Hydrogens, oxygens all have 2 bonds and 4 dots. Only thing left over is to see if there's any leftover electrons that would go on sulfur. And so we have used 8, 8, and 8. So we've used 24 electrons. So when you subtract 24, you end up with 2. Those 2 go on to sulfur. And so sulfur gets a lone pair. And we drew sulfite last week. This is pretty much sulfite with just, instead of an extra lone pair, it's got a hydrogen connected to it. So you got a lone pair there. So that's all the electrons. If you double check, 8, 16, 24, 26. Once the Lewis structure is finished and we've drawn all the bonds and the dots, we can then count sigma and pi bonds. 2 ways to look at this, and I'm going to look at it from single and double bonds. Okay, so I've got single bond, single bond, single bond, and single bond. So I have 4 single bonds in our drawing. And every single bond, each of the single bonds is what kind of bond? It is a sigma. And so those 4 single bonds are 4 sigma bonds, because the first bond between 2 atoms is a sigma bond. Then we have 1 double bond. And the double bond is 2 individual bonds. One of them is sigma, and one of them is a pi bond. So there's a total of 6 lines in our drawing, so 6 bonds total. 5 of them are sigma, and 1 of them is pi. That's the valence bond theory designation, molecular orbital theory designation. It just differentiates between a bond where the orbital is directly between the atoms, or a bond where the orbital is above or below the atoms, like outside of the same plane. Okay, so then we're going to do the hybridization. We could do the hybridization of the oxygens or the sulfur. And I'm just going to pick sulfur. But anything that has more than one bond is hybridized. So all the atoms except hydrogen, we could figure out what happens to their orbitals, because it's just what happens to its orbitals. So we're just going to figure out what happens to sulfur's orbitals. Okay, so sulfur, it has 1, 2, 3 sigma bonds. So we're not going to count the pi bond because it's not formed with hybrid orbitals. And then it has 1 lone pair. So the sulfur atom needs to use 4 of its orbitals to form 4 hybrid orbitals. Okay. What is the hybridization called for 4 orbitals? Yep, we make 4 sp3 orbitals on sulfur. Those orbitals, those hybrid orbitals, will move into what kind of geometry? Tetrahedral. So the actual hybrid orbitals will have a tetrahedral geometry. Tetrahedral geometry for the hybrid orbitals. So that would spread, being in the tetrahedral geometry, there would be an orbital for the lone pair. There would be an orbital that goes out and bonds this oxygen to that oxygen and to that oxygen. They would be spread out in a tetrahedral. But one of the orbitals has a lone pair and we cannot see it. And so the molecule, the shape around the sulfur would be trigonal pyramid geometry around the sulfur. So around the sulfur atom, it's going to be trigonal pyramid. So if we redraw it, one of the easiest ways to draw a trigonal pyramid is to put the lone pair at the top of the drawing. That's just, to me, it's the easiest way. Okay. I'm going to draw it just using regular lines, just angled instead of wedge, but I'll show you the wedge way also. And so we can do it doesn't matter which one of these spots you put the O or the OH, because they're all pointed down. So they're all beside each other. This O is next to that O and next to that one, and that one's next to that one, and they're all next to each other because they're the bottom of the pyramid. The bond angle between these is less than 109. So it might be 108, it might be 107, it might be 107.8. It's just somewhere less than 109 degrees. So a tetrahedral geometry with no lone pairs is about 109.5. But that lone pair up here, it expands and it pushes these bonds closer to each other, just a little bit closer. Right. If you drew it using the wedge to show what's coming towards you, I'm gonna choose to do the double bond in the same plane of the paper to make it easy for myself. And then you do the one in the what looks like the middle, you do it kind of bold, and it's illustrating that it's coming out of the paper. And it has an O bonded to an H, and there's 2 lone pairs. And then the other one, instead of a bold wedge, it's a dashed, and that is illustrating that it's going behind the paper. And that's bonded to the O, which is bonded to the H, and lone pairs. Both of these are showing the same thing. I chose to put my double bond over here because I did not want to do a bold double bond or a dashed double bond. Okay. And you would put the bond angle less than 109. Okay, last thing, is it polar or non-polar? There's two things. Okay, it's not diatomic because we're just looking at simple molecules. After diatomic, it says all acids all acids are polar. You don't have to go any further. It does fit one of these, but the problem is not all acids have lone pairs. If it's sulfuric acid, phosphoric acid, nitric acid, nitrous acid, chloric acid, hydrochloric acid, any acids, all acids are polar. Because the hydrogen has to be partially positive. And the only way for hydrogen to be partially positive is for it to be part of a polar bond in a polar molecule. All acids are polar. If you didn't see that, if you see those four words there, and you went into here, you would see that this one here, all atoms around it are the same element, and there's no lone pairs. There is a lone pair. But also, these oxygens are not the same. That is an O, and that is an OH. O and OH are not the same thing. Okay. It matches this one here, same element, kind of, but it really is not. They're really different elements because it's O versus OH, and it has lone pairs. So it's polar. You're going to put the partial negative on the most electronegative atom, which is oxygen, and there's 3 of them. And so I'm going to put a partial negative on each of the oxygens to show the polarity. And then anything that is covalently bonded to is partially positive because it pulls the electrons in any bonds that it has closer to it. And so that means every bond that it takes part in is polar. And so this oxygen is bonded to that sulfur and that hydrogen. So the hydrogen is partially positive. The sulfur is partially positive. I have just put that on that sulfur. I don't need to write it again. This being polar just makes that even more partially positive. This one, even more partially positive. This hydrogen here is partially positive. Every atom in sulfurous acid has a partial charge. Everything's polar. So